Hello, I'm Robert Morrison, and today we're going to take a look at Newton's second law. The write-up for this lab can be found in our Physics Through Inquiry manual. All you're going to need for this particular write-up is a mass, a spring, a right angle clamp, a rod stand, a short rod, a motion sensor, a force sensor, and of course an interface for collecting data. Let's take a look at the setup. We'll collect some data and talk a little bit about how you might use this with your students. So I'm going to go ahead and use my rod stand here. I'm going to move it to the edge of my table. I'm going to take my right angle clamp and I'm going to place it about halfway down, whatever's convenient for you height-wise. If you want to use a large table clamp, you can do that too, depending on your table, of course. I'm going to make sure my shorter rod here has enough over the edge of the table so that I can mount my force sensor, which I will do next. And I'm using the hook on the end of that force sensor. I'm going to make sure that's pointing down and right over the edge there. And then I'm going to take that and connect it to my interface. And that also ensures that I have power to that sensor. So I'm going to take my mass and my spring next. I'm going to connect the mass to the spring first. And should just take a second. Okay. And I'm going to attach that to my force sensor. I'm going to let that hang down until it is motionless, or close as I can get. Excellent. Okay, so now I have my hanging mass. Now what I'm going to do, you'll notice on the screen I have a force on my force sensor, obviously, from the mass. And since I'm interested in the net force, I'm going to go ahead and zero my force sensor with the mass attached. Great. Okay, so I'm going to attach my motion sensor. And this is one of the trickier bits. You want to make sure that you align this very carefully underneath the mass. I'm using a flat bottom mass so it's easier to pick up with the motion sensor. Also a rounded bottom mass would work well. You just want to make sure it's not something that's got an angle that's going to send your pulses off in an odd direction from your motion sensor. So I'm going to go ahead and connect that to my interface. I'm going to place that right underneath my mass. And I want to make sure it is aligned very carefully and pointing directly at the mass. And just to be sure, I'm going to tip the motion sensor a little bit away from the table so I'm not catching the edge of the table. And then I'm just going to align down the spring to make sure I'm right under the mass. Just a little bit. And I'm also going to make sure that my motion sensor is set in the cart position because I'm looking at a small object at a very close range. And that's pretty much the setup for this experiment. Now, I just want to make sure that I am not going to ever get closer than 15 centimeters to that motion sensor. So when I go and I start oscillating that mass, I'm actually going to pull it down a little bit until it gets just over 15 centimeters, and I'm going to let go. So that ensures that the oscillation will never get closer than 15 centimeters. So now I'm going to take a look at that position versus time. To do that, I'm going to build a position versus time graph. And I'm going to say OK. And we're almost ready to go. The last thing I want to do is I want to make sure that I'm collecting data at about 20 samples a second so I get a nice smooth curve. Let's go ahead and change that to 20. Excellent. Okay, ready to collect data. I'm going to go ahead and start. And you can see we are collecting data. And we usually start with position versus time to make sure that students get a really good physical connection between what's going on with the mass and the data they're seeing on the screen. So we'll go ahead and stop. And even though we've just looked at position versus time, since we have passport sensors, it's collecting all that data for each one of these sensors. So all the force data, all the position, velocity, acceleration data is being collected in the background. So let's go ahead and blow that up. Take a look at that data. Looks good. And now in this write-up, what we do is we have students compare position versus time and versus force versus time, velocity versus time, and acceleration versus time. So let's go ahead and take a look at one of those graphs. I'm going to take position in a graph, and I'm going to look at force pull positive. The alignment of the force measurement is fairly critical because we're using the motion sensor as our basis of motion. So anything moving away from the motion sensor is in the positive direction. So what I want to do is make sure that the force is also in a positive direction or aligned in the same positive direction. So the way we've aligned this force sensor is by virtue of what you're doing with the sensor. If you're grabbing onto the sensor, if you are pulling with the sensor, that's a positive pull. If you are pushing with the sensor, that's a positive push. So we want to make sure our pull is aligned with our motion, So we're going to use pole positive as our force. And now we're going to go ahead and take a look at those graphs compared. You'll see that the axes line up fairly well. If you need to, you can go in and adjust them. But this is what we'd expect to see. In fact, that the position data is about 180 degrees out of phase with the force data. So good start. So let's take a look at what happens with velocity versus time. We're going to go ahead and build a new page. Look at velocity versus time. And again, that pole positive. And take a look at those graphs. And you can see that when the force is at the peak, you're going to have the velocity at its transition point here. So that is essentially what we'd expect to find. So it's about 90 degrees out of phase. And if your students aren't familiar with periodic motion, you might not use the terms phase. You might want to say that the maximums don't line up or that they're not quite in alignment. But we're going to take a look at one more, and that is acceleration and force. So let's grab those. Again, pole positive. And compare. And now we can see there's a very good relationship going on here where we have peaks of force data aligning with the peaks of acceleration data, and that's what we'd expect. So during the write-up of this particular lab, what we have students do is take random points and compare them. And they want to make sure they're getting them out of one of these smoother areas, not one of these odd spikes, but make sure that they get some nice data and compare that. And what we normally have them do is compare 3 points and maybe average those 3 points of force divided by acceleration data. So we're going to have them compare that to a force versus acceleration graph. Let's go ahead and bring that up. And we're going to say force pole positive and acceleration on the same graph this time. And we just verify that force is in fact the y-axis and that x is in fact on the acceleration. So we're going to go ahead and say OK. As you can see, a little variation, that is a fairly linear relationship of force versus acceleration. So now the students are getting an idea that there is something going on there. So let's go ahead and take a look at the slope of that line, or slope of the best fit line for that graph. And we can see the slope comes out to about 0.205. And that is excellent, in fact, because the mass that we're hanging here is, in fact, a 200-gram mass, and the spring is about 10 grams. So we'd expect about a third of that to be contributing to the mass of the total system. So very good results indeed. And your students with this kind of a system can expect similar results when they're doing it. You may notice it gets a little chunky in there, but overall it averages out very nicely. So we have your students discovering for themselves that force over acceleration is related by virtue of mass, or their proportionality constant is mass, or F equals ma, Newton's second law. We use this particular system because we want students to see that this applies to a system where the force is constantly changing. So up until this point in this particular manual, students have been using the carts and tracks, and they've been seeing things in a constant force environment. We want to make sure that they know that that law applies to a system that's in constant flux or constant change. Okay, well, we hope you enjoy this lab, and we hope you have a good time with your students. We appreciate your feedback, so please send it in, and we hope you have a great time with this lab. Thank you very much.